Hello and welcome. In this video, I'm going to analyze a regenerative Rankine cycle. There are three different pressures in this cycle. One is 9 MPa, that's the boiler pressure. Another pressure is 0.7 MPa, 700 kPa, that's the feed water, the bleeding pressure, the pressure that the steam is bled from the turbine at. And finally, there is a third pressure is the condenser pressure. If we draw the cycle on a TS diagram, so this is our P pressure of the boiler, and this is the bleeding pressure, and this is the condenser pressure. Now notice that in this because of the bleeding from 2, the steam bled from state 2 is mixed with liquid water at state 5 coming from the first pump to make the water heated to state 6, and that heating occurs internally. So after pumping the water to the boiler pressure, external heating takes place from 7 to 1. This is where external Q dot in goes in, and of course Q dot out takes place at the lower temperature. So if you think of the efficiency, thermal efficiency, which is 1 minus Tc bar over Th bar, the approximate efficiency of the cycle, depends on what is the Tc bar and Th bar. Tc bar is relatively constant at a very low condenser temperature, and Th bar, notice, is now between temperature at 7 and 1 as opposed to 5 and 1 if there are no bleeding, if there are no feed water heater. So this is called regeneration, when you take heat from one part of the cycle and put it on another part. By doing so, we have increased Th bar without changing Tc bar. Therefore, you can see we expect the efficiency to increase. Okay, so let's get started with the solution. So to expedite the video, first of all, if you go to the test step page, the correct app should be follow the open specific branch, and vapor power, which is the PC model, will be our model to use. Now, it is assumed that you're familiar with, first of all, I would say I highly recommend to go over at least one simple problem. Say this one. This particular problem is a simple Brayton cycle. So simple Rankine cycle. You should go over this before modifying any cycle. To expedite the solution, I have already solved the problem on a different window, and I'll just walk you over through every step I have followed. First of all, in the I/O panel, I've declared some overall variable, the boiler pressure. As you recall, there are three different pressures. The boiler pressure is here. Then there is the maximum temperature in Kelvin, the bleed pressure, 700 kPa, and the condenser pressure. I want to keep the variable name small, that's why I named them in this manner. Now in the state panel, state 1 is quite simple. Pressure 1 is boiler pressure, temperature is known, and I'm assuming a mass flow rate of 1 kg per second. Why? If you go back here, you'll notice that the mass flow rate is not supplied, the power produced is supplied. So what we're going to assume is that the flow rate is 1 kg per second here, and based on that, we'll figure out what is m.2. This is an unknown. So how do we find m.2? Notice that the feed water heater must produce water, saturated water, in an ideal regenerative cycle. So at state 6, quality is 1. So that's what makes our bleeding amount. That determines the bleeding amount. So as you can see, if we do a heat balance on the open water heater, then we can write m.2 must be times enthalpy plus what is m.5, which is coming in here, which is m.1 minus m.2 times H5. This is the energy entering through this pipe, must be equals, and this flow must be equals m.1 times H6. So this equation gives us a formula for for m.2, and that's what we are going to plug in. So m.2 if you write down what that is, you can simplify and show that it's H6 minus H5 divided by H2 minus H5. Okay, armed with this theoretical information, we go back to state 2, and that's what we've done. State 2 is the bleeding state from the turbine, P bleed, pressure is P bleed, and m dot, by the way, I have already calculated. When you write the equation, you'll find the equation is not evaluated. So just to remind you that whenever we put mouse over a quantity, you should see help in this zone. So for instance, if I go, so help will be appearing here. Please keep an eye right here. Let me see if I can go. Okay, so when I point the mouse over there, you can see when I put the mouse over m dot 2, you can see what I entered there. And that's the equation we just derived in the PowerPoint slide. Of course, when you calculate state 2, you'll find it's not evaluated because we don't know at this point what is H5 or H6 is. Of course, I finished the calculation, that's why this is in green, otherwise it will be in white background. Okay, now let's move on for state 3, which is state 3 is the turbine exit state. Again, it's isentropic. By the way, the bleeding state is also isentropic, so I use that. It's isentropic, and the pressure is same as the condenser pressure. And of course, m dot 3 now is written in terms of m dot 1 minus m dot 2. We want to keep our number of variables minimum, so that in case we want to change a variable, it's very easy to do a parametric study. So we are writing m dot 3 in terms of m dot 1 and m dot 2, and those will be our only two unknowns as far as mass flow rate is concerned. And m dot 1 is already known, by the way. We assumed it to be 1 kg per second. Okay, so state 4 is the condenser exit, and again, condenser exit will be having a quality of 0 by definition of an ideal cycle. It's saturated liquid, and the pressure is of course condenser pressure. M dot 4 must be equals m dot 3. So state 5 is the exit state of the pump, first pump. So the pressure should be raised to the bleed pressure because there is a mixing chamber. The feed water heater is after that, and m dot 5 is same as m dot 4, which is same as m dot 3. So you're keeping the variable limited to m dot 3. Also, it's isentropic, therefore S5 equals S4. If you go to state 6, we find it's the exit state of the feed water heater. Again, the pressure is known and mass flow rate is known. Also, the quality we know has to be 0, so the state is completely determined. State 7 is the second pump. Again, it's isentropic, as you can see here, and the mass flow rate becomes same as state 1. Same with state 6, by the way, because if you look at the diagram, open feed water heater, state 2 and state 5 mix to produce state 6. And finally, from state 7, we have the boiler taking us back to state 1. So state 7 is our last state after the second pump. So once all the states are evaluated, we can go to the graphics panel and verify that this is exactly as we anticipated, except the pump, across the pump, the change of state is almost invisible on a TS diagram, because if entropy doesn't change, T doesn't change. When we draw the diagram ourselves, we exaggerate this difference. So actually 4 and 5 and 6 and 7 are almost on top of each other. Okay, so now let's go and analyze the devices. Okay, so we go to the device panel. The device 1 is our turbine. So state 1, you can see that state 1 is our inlet, and 2 is our bleeding, and 3 is our exit. Once we select them, Q dot equals 0, so next external work is found here. Let's see, the device 2 now is the condenser going from 3 to 4, and the heat transfer is calculated. Device 3 similarly is the first pump, and work is calculated between, it operates between state 4 and 5. Device 4 is the mixing chamber, which is the feed water heater, where state 2 and state 5 are mixing to produce state 6. And of course, to choose that a device, we got to choose the device type to be multi-mixing. That's the only manual part that I haven't shown here. And finally, this is our device 4. No, sorry, there are 2 more devices. Device 5 goes from 6 to 7, and that is our second pump. The pump work is found, negative. And this is the boiler, 7 to 1. Therefore, the heat transfer in the boiler is calculated. So recall that all these calculations are based on a mass flow rate of 1 kg per second. M.1 was assumed to be 1 kg per second. With that, the cycle panel, we see that the thermal efficiency has been calculated, also have been calculated W.net. But of course, if I change the mass flow rate, it should not affect the efficiency, but it should affect the net output. In this particular problem, the net output is given as 100 megawatt. So therefore, we can find the mass flow rate by dividing 100 megawatt with this number. So let's go and do so in the I/O panel. So let's isolate our equation. So our mass flow rate, suppose we call it m dot, must be equals what? 100 megawatt means 100,000 kilowatt divided by W dot net 1, that is the variable name, and that should produce the mass flow rate right here, 87.75 kilograms. Okay, now suppose we'd like to know what would be the thermal efficiency if there are no bleeding at all. So how can we stop the bleeding process? If we go to state 2, that's where the bleeding was taking place, if you recall. So if I set m.2 to 0, then that means I'm not bleeding at all. Now if I run a super calculate, let's go and check the cycle panel and look at the efficiency. Look, the efficiency has gone down.